Lenz's law states that the induced current in a loop is going to be in the direction needed to oppose the change in the external flux that is passing through the loop. So what does that mean? Well, let's start with an example. Here is my external magnetic field. Here's my external magnetic field. And there is my loop. So what I want to figure out is what is happening with the flux. Is the flux increasing or decreasing? And remember that my goal here is to figure out the direction of the induced current. I know there's going to be an induced current if the flux is changing because of Faraday's law. Faraday's law tells us that any change in magnetic flux induces a voltage. And if we induce a voltage, if there's a voltage applied to this loop because of Ohm's law, V equals IR, if there's a voltage, there's going to have to be a current, assuming, of course, that I'm dealing with a conductor, which I am here. This is a conducting wire loop that I've got. Okay, so my external magnetic field is pointing straight up as I'm viewing it. It's out of the screen as you're viewing it. And my situation is going to be, I'm going to take my loop and I'm going to rotate it like so. Okay. So if I do that, if I rotate it like so, that's going to be less flux passing through it. The flux is going to decrease. Okay, so since the flux is decreasing, what does that mean? Well, the simple rule is that if the flux is decreasing, then the induced magnetic field at the center of the loop has to be parallel to the external magnetic field. So let me say that again. If the flux is decreasing, the induced magnetic field at the center of the loop has to be parallel to the external magnetic field. And that's what's happening here. The flux is decreasing as I rotate it. So I take my right hand, you point your thumb in the direction of the magnetic field, okay? And then the fingers, and I said the magnetic field, I meant the induced magnetic field. It points in the direction of the induced magnetic field. And then the fingers curl in the direction of the induced current. So in this situation where I'm rotating my loop like this, that leads to a counter, as we're viewing it, a counterclockwise current. Now, let's look at the other situation. I did the situation where the flux was decreasing. What about when the flux is increasing? Okay, so I'm going to start here, and I'm going to go to here. Okay. So if I'm over my external magnetic field as I've drawn it, there we go. I go to there, you can see I'm going to increase the amount of flux passing through it. So what happens there? Well, if the flux is increasing, then the induced magnetic field will be anti-parallel to the external magnetic field. So it's going like this, starting here, going to here. So anti-parallel means I've got to point my thumb down. Let me get this all right, get the angle, there we go. My thumb is down, and my fingers are curling in the direction of the induced current. So in this case, clockwise. So here, in this situation, I get a clockwise current. Now, I want to stress what what kind of the situation is, how we're viewing this. We're looking at increasing flux or decreasing flux. That's your first step. Determine, is the flux increasing or is the flux decreasing? That allows you to determine the direction of the induced magnetic field, and then you use your right-hand rule. This is a new one we're talking about. The thumb points in the direction of the induced magnetic field, okay? And your fingers curl in the direction of the induced current in that loop.